Are you all ready for a second day of problems involving series? I know I'm ready for that, so let's get going. More Fast and Furious, but the important part here is that around the next corner we're going to estimate that the distance from the outer wall is this function gt, where g is the number of feet from the outer wall, just like yesterday. What is the exact equation of g? And Hans suggests that Sean must alter his path given by h, which is 1/6 t gt. So write the first three terms in the general term for h. C, now C is really a lot of work. Around the third term, you're going to get mt, which is given in sigma notation. So find the interval of convergence. D, short on calculation time, you're only going to use the first two terms to estimate m of 5.8. And then it says to use alternating series error to find an upper bound for the series. And you're then going to use your bound to create an interval for Sean's ideal distance from the outer wall. Okay, so that is a lot. Letter A, what is the exact? So whenever a question in the series section asks you for an exact equation, there are only two things that could be going on. Number one, maybe the series you're looking at is going to be either that some form of e to the x, maybe it's some form of cosine, maybe it's some form of sine. And number two, maybe it's a geometric series. So you need to be familiar enough with these series to know, are you looking at sine? Are you looking at cosine? Are you looking at e? Are you looking at a geometric series? And as I'm looking at this one, I notice that to get from the first term to the second term, you need to multiply by -2t minus 3. And then to get from the second term to the third term, you're going to have to multiply again by -2t minus 3. So the fact that this is a series constructed out of repeated multiplication tells me that this is a geometric sum. Once you know it's a geometric sum, then you're just going to use the properties of geometric sums. For example, a geometric series or a geometric sum is always equal to the first term over 1 minus the ratio. So you will notice in the previous line I have written that the first term is 1, clearly, and the second term is -2t minus 3. It's always nice with a geometric series when you've got that first term is 1, because then that second term automatically turns into the ratio. Anyways, we know what the first term is. We know what the geometric ratio is. So that means that the series is going to add up to a over 1 minus r. In other words, the series is going to add up to 1, which is the first term, over 1 minus the quantity -2 t minus 3. Now that may or may not be a algebra problem for you. Hopefully not. I mean, you're in calculus after all. So when you simplify that, you're going to get 1 over 2t minus 5. Ooh, where'd we go? There we go. 1 over 2t minus 5. So that's our geometric sum. That's what all of those infinite number of terms are going to add up to. Of course, they're only going to add up to that in the interval of convergence for t. Okay, let's go on to letter B. Hans suggests that we have to follow this new function 1/6t gt. So we're going to start off by writing the series for gt. Here's that series for gt. And then to gently turn this into the series for ht, we're just going to multiply each term by 1/6 t. So here you see, on the left side, I'm multiplying by 1/6 t. And on the right side, I have that 1/6 t just waiting to be distributed into the polynomial. There's that 1/6 t right here. So we're waiting to distribute that. Let's distribute that, and we get this series. Notice here that h of t is equal to 1/6 t gt. So h of t is equal to this series right here. We've got this all linked up with equal signs. So that tells me what h of t is. Also notice that I didn't bother distributing the t. You do not distribute into, definitely, you don't distribute into a square. So this is going to be fine. In fact, it's really doubtful that you're going to have an AP test where you're going to have even something close to this kind of algebra problem. So we're good here. This is all we really need to do. Letter C, we have this new series MT, and I notice that MT is written in sigma notation. And whenever I see something in sigma notation, it tells me that whoever wrote this question is probably hiding something. I don't know what they're hiding, but, well, maybe I shouldn't say probably, but it's a good way to hide things. Like maybe this is a geometric series. So the first thing you want to do is whenever you see something in sigma notation like this, is just to write it out. Let's see if this actually is a geometric series. You'll notice I wrote out MT over here, and no, that doesn't look like a geometric series. If it's not a geometric series, then we need to go on to the ratio test. So let's get started with the ratio test here. First thing, here is the ratio test as it applies to a power series. Now, I always tell my students that you've got to force that ratio, the limit of the ratio anyways, you got to force that to be less than 1. Because when it's less than 1, when the limit is less than 1, then you're going to create the interval of absolute convergence. Now, you're going to algebraically put together this series, or this limit. Notice that this right over here, that is a reciprocal of the n plus 1th term. That is the n plus 1th term. And this one is a reciprocal for the nth term. So if you've done this more than a couple times, you know that multiplying by the reciprocal is the same thing as division. So when we simplify this next, we're going to take that basic form and we're going to kind of group things together that are kind of alike. So the first thing I'm going to group together are the 2 to the n plus 2 over 2 to the n plus 1. Those are alike. When I reduce that, I'm just going to get 2. The next thing that's alike is the root n plus 3 over root n plus 4. Remember, the shortcut way of thinking about this is one big square root of n plus 3 over n plus 4. So those go together. Not a whole lot of simplifying other than putting them in the same square root. And the last one is going to be the t minus 6. You've got t minus 6 to the n plus 1 power over t minus 6 to the n power. The n powers are going to cancel out, and you're just going to get t minus 6 to the first power, or just t minus 6. Running out of room here, so let's go up there. And what you see here is that this right here, that just simplifies to 2. And then this over here, that simplifies to t minus 6. But we were in absolute values, so this t minus 6 needs to stay in an absolute value. And then the only thing left with a limit is the square root of n plus 3 over n plus 4. So the limit of the square root is the same thing as the square root of the limit. So all you really need to do is figure out what is the limit of n plus 3 over n plus 4. that, of course, is 1. So you get 2 absolute of t minus 6 multiplied by 1 is less than 1, which is great because this is or once you divide by 2, you get the absolute value of t minus 6 is less than 1/2, and that is of the form, what is this? X minus the center is less than the radius. Okay, so that didn't stick very long, but that once you have variable minus the center is less than the radius, then you don't actually have to do a whole lot. You just need to do center minus the radius. 6 minus 1/2 is 12 minus 1/2, so 11 over 2. And then 6 plus 1/2, that's 12 over 2 plus 1, so 13 over 2. So this right here, 11 halves to 13 halves, that's our interval of absolute convergence. We have that interval. Now you've got to check the endpoints. Every time you use the ratio test, you've got to check the endpoints. Let's start taking a look at the endpoints here. So we're going to do endpoint convergence, starting with 13 halves. So when you substitute 13 halves into the series for t, substitute t equals 13 halves, you're going to produce, what is this? 2 to the n plus 1 multiplied by 1/2 to the n over root n plus 3. Now 2 to the n plus 1 is the same thing as 2 to the n times 2. And then 2 to the n multiplied by 1/2 to the n, that's just equal to 1. You may want to think about this as 2 to the n multiplied by 1/2 to the n is the same thing as 2 times 1/2 to the n, so that entire thing is just 1. So after you substitute the series, or substitute 13 halves, you just get 2 over root n plus 3. So the series becomes a series of 2 over root n plus 3. Now, endpoint convergence basically says, well, what happens at 2 over root n plus 3? Is that a converging series or a non-converging series? Well, to me, that looks like a power series, or it looks really close to a power series. No, I'm sorry, it looks like a p-series. Looks like a p-series, so we're going to use the LCT to compare 2 over root n plus 3 to the p-series 1 over n to the 1/2. So LCT says you take the two series and you compute a limit as n approaches infinity of the two series and ratio. If I do that, that's the same thing as the limit as n approaches infinity of 1 over root n over 2 over root n plus 3. A little bit of algebra. And that gives me 1/2 root n plus 3 over n. And as we saw before, root n plus 3 over n, if I take a limit as n approaches infinity, I just have to take the limit of n plus 3 over n, which of course is just equal to 1. So this limit is 1/2 times 1, which is just 1/2. LCT says that if the limit is any number, then that means that the two series are going to do the exact same thing with respect to convergence. So they're either both going to converge or they're both going to diverge. Well, we already know that one of the series, we already know that one of those series diverges. So the other one, the one that we're really interested in, 2 over root n plus 3, that has to diverge as well. Okay, what about the other endpoint, t equals 11 over 2? Well, at t equals 11 over 2, we're going to substitute 11 over 2 for t into this general term of the series, and you're going to get 2 to the n plus 1 negative 1/2 to the n power. And we're going to do a lot of the same simplification techniques that we did before. That 2 to the n plus 1 is 2 times 2 to the n. That negative 1/2 to the n, that's the same thing as negative 1 to the n multiplied by 1/2 to the n. And 2 to the n multiplied by 1/2 to the n, you know that's 1 already. So this series, the general term of this series is negative 1 to the n multiplied by 2 over root n plus 3, which means a series is an alternating series. So if that's an alternating series, we just need to utilize the Leibnitz test to figure out whether this converges or not. Leibnitz test says that if you take the absolute value of the general term and that goes to 0, if the limit of the absolute value of the general term goes to 0, like this one does, then the series is going to converge. Now be careful, because that is a lot of the same words that we would use for something like the nth term test. So you really got to know which test are you trying to do here. If it's the Leibniz test, 0 is a good thing. If it's an nth term test, 0 is not a good thing. So we know that 11/2 converges, 13/2 doesn't converge. So the interval of convergence is 11/2 closed and 13/2 open. There's our interval of convergence. There's our ratio test. Short on calculation time, Sean uses the first two terms of the series of mt to estimate its position, t equals 5.8. Use an alternating series bound to find an upper bound for this error, p1 5.8 minus m 5.8. And then you're going to use that bound to create an interval for Sean's ideal distance from the outer wall. Now, as you do this one, you've got to be aware of the fact that you're doing a problem that has to do with error. So even though it says to use the first two terms of the series, you really want to look at the first three terms, because in an alternating series, the error is that third term. So I'm going to write the first three terms of m. Here they are. Now that I have the first three terms, I'm going to substitute into all of them, but for the error, I'm just going to look at the first two terms. So let's take the first two terms and we'll substitute 5.8. So here is the first two terms. Substituting 5.8 gives me, what is this? 2 over root 3 plus 4 over root 4 multiplied by negative 1/5. And I know this is not the calculator part of the test. If this was an actual AP test, this would be something which you can calculate, using pencil and paper only. But since this isn't the actual AP test, we're going to do this with a calculator and figure it out. Well, we get 0.75470. Okay, so that is the estimate for his distance for the wall. Remember, it's an estimate because we only use the first two terms of the series. Okay, for the error bound, let's substitute 5.8 into that third term, the first unused term, and let's get an absolute value of that. In an alternating series, the error is always less than the absolute value of the next term of the series. And by next term, we mean the next term when you substitute 5.8. It's always going to be a number. It's not going to be an expression. So we're substituting 5.8 into the very next term of the series. I also tell my students that when you see P1 5.8 minus M 5.8, you are not to calculate that. That is just a phrase translated from math that means error. So that says the error is less than, there's that next term, we've substituted 5.8. Again, since this is not the AP test, we're just going to use a calculator to figure that out. And we get 0.14310. That's kind of like our margin of error, really. Using that margin of error and our point estimate of 0.754, we can create an interval of possible values or plausible values for the distance from the wall. So we're saying the distance of the wall is the same thing as the estimate plus or minus the error. If I subtract, I get 0.6116. If I add, I get 0.8978. That means that the distance from the wall should be between 0.6116 and 0.8978 meters. So that's error. Error is a really big subject, but it's only really a couple of points on the AP test. At least it's only a couple of points on the multiple choice or the free response section. So let's take a look at the key ideas that we did here. First of all, always check if a series is geometric because things are easier for a geometric series. The interval of convergence is easier. The error is not the error. Writing out the series is easier. The sum of the series is easier. Remember that a geometric is going to converge to a over 1 minus r, and it's only going to converge if the ratio is less than 1. You use that absolute value of the ratio less than 1. You're going to use that to create the interval and the radius of convergence. Now, new series can always be formed by multiplication of monomial factors. It'll be very rare when you're not multiplying by a monomial, like a binomial or a trinomial. I don't expect that happening except very rarely. And of course, if you do need to find an interval of convergence and you don't have a geometric series, this is when it's time for you to use a ratio test. The ratio test will give you the center, the radius, and the interval of absolute convergence. And then you need to check the endpoints. I have a note here to look at the flow chart for series. We looked at that during class. Please look at that so you can kind of see how the flow of things go. That's why they call it a flow chart. And if you do utilize the ratio test, you have to test the endpoints. If it's a geometric series, you don't have to test the endpoints because the endpoints will never converge on a geometric series, which is why the geometric series is so much easier than a non-geometric series, or another reason why. Go ahead and copy that down. I'll wait a minute or so, or I guess you can pause it actually. So pause it right here and copy those down. Cool. Let's look at check your understanding. The function f is defined by 1 over 1 plus m cubed, and it is given by, look at that, they even gave you the series. In my brain, I'm looking at that and I'm saying, hey, that is a geometric series. First term is 1. Repeated ratio is negative x cubed. Okay, they also give you an interval of convergence. Look how nice can they possibly be? So for letter C, find the first 4 non-zero terms of the integral. Letter D, use those first 3 terms to approximate the integral evaluated from 0 to 1/2. And then what are the properties of the terms in the series that guarantees that the approximation is within 1/10,000th of the integral? So we're going to take a look at those. First of all, for letter C, it's just an integration. When I see students try this, sometimes they try to integrate. They gave you what f of x is, and they try to integrate f of x, or in this case f of t, which of course is a wrong idea because that is an integral that you can't evaluate using the techniques of calculus BC. I'm not saying you'll never be able to integrate that. I'm saying in calculus BC, you're not going to be able to integrate that, and they know that. So rather than getting yourself into a sticky situation, you do have an alternative here, and that alternative is, instead of integrating that function, why don't you just integrate the series? It's also easier to integrate because it's just a term-by-term antiderivative. So the antiderivative of 1 is t. The antiderivative of t cubed is 1/4 t to the 4th. I'm sure you know all of that already. And then you're going to substitute x, substitute 0, and then take a difference. And that gives you, look at that. All you do is change all the t's into an x. And that's your series. It even does a nice job with the general term. So that's part C. Not really a whole lot to it. Part D is the part that usually gives students headaches because it is asking for error. So first of all, we're going to use the first 3 terms of the series here. So I'm going to isolate the first 3 terms. I notice that I have an exactly equal to sign. I'll fix that. That really should be approximately equal to. And then I'm going to change all those x's. And I mean this x, this x, this x, and this x. I'm going to change all of those into a 1/2. Changing those into a 1/2, that gives me the ability to get a estimation. I got 435 out of 896. That is asking a lot of you to, go to 2 to the 7th power, multiply by 7, and then turn everything to a common denominator. So if, you are running short on time, or even if you're not running short on time, just leave the answer like this. That is the correct answer. Definitely, no one would expect you to get 0.48549. That's just because I had a calculator handy. Did you notice something about this series? Did you notice that it's alternating? And if a series is alternating, that means the error should be less than the very first term that is unused. Which means that, well, first of all, that's a property that they were looking for. They're saying this is an alternating series, so we know how to calculate the error for an alternating series. The error for an alternating series is just the first unused term. Just like with that previous one, it's probably unlikely that they're going to ask you to evaluate 2 to the 10th power. It happens to be 1024, so 10 times that is 10,240, which happens to be less than 1 over 10,000. So the error is less than 1 over 10,000. So that's it. That's our second day worth of series questions. Remember, I'm not trying to pretend that this is going to be the only kinds of questions that they're going to ask you on the series questions. There's definitely going to be, hopefully not, but if they do throw something at you that isn't covered here, chances are other people are going to have problems with it too. But don't count on anything like that. Should you have these basics down, you're gonna do well. I know you're gonna do well. If I can give you any last piece of advice here for your series, it would be to make sure you memorize at least those 4 series that we talked about, and also make sure that you have the geometric series really in your head whenever you're looking at a series. Try to look at it with the lens of, is this a geometric series or not? Okay, guys, I'll see you later. Have a good day.